Hydronic systems are the backbone of modern heating and cooling design, moving heat efficiently and economically using liquid, most often water. Think of a hydronic system as a heat transfer machine, carrying heat into or out of a space according to the building's demand and your chosen control settings. Hydronics works on simple physics. When water absorbs heat, it expands and carries that energy through pipes to coils, radiators, or other heat exchange surfaces. Designers create reliable systems for single-family homes or central plants, but effective air management is crucial for optimal performance. Without proper air management, air pockets can form inside pipes, leading to noisy operation, unbalanced flow, poor efficiency, and even shortened system life. Therefore, good design always begins with controlling and eliminating air to ensure smooth and silent operation. Closed systems utilize two main strategies for air management: air control and air elimination. Air control traps air and routes it to a high point for venting, while air elimination uses air separators and automatic vents for continuous removal. These techniques ensure water circulates fully and heat transfer surfaces remain effective, preventing issues like noise and reduced output. A closed hydronic system is completely sealed, minimizing the need for makeup water, which is crucial because new water introduces oxygen that causes corrosion. By keeping the system sealed and pressurized, you dramatically extend its service life and gain performance benefits. Pressurization allows higher operating temperatures and greater temperature differences, which can reduce both pipe size and pumping costs. The pressure in the system is managed by a compression tank, which absorbs water expansion as the temperature rises. Since closed systems don't leak by design, circulating pumps use mechanical seals instead of old-style packing glands that rely on leakage. There are 4 types of pressure you'll encounter in a hydronic loop: initial fill, static, operating pressure increase, and pump pressure. Initial fill pressure is the cold fill that ensures water reaches the highest point of the system, with at least 4 psi at the top. Static pressure is caused by the vertical height of the water column. Roughly every 2.3 feet of height equals 1 psi. Operating pressure increase is created when the water expands and compresses the air in the tank. Pump pressure is the differential created by the circulating pump itself, driving the flow. When filling the system, 3 goals matter: fill it completely, provide that minimum 4 psi at the top for venting, and maintain pressure above the vapor pressure of water to prevent cavitation. Since water can't be compressed, we use a compression tank to absorb expansion. The tank size depends on the system's total water volume, the temperature rise, and the chosen pressure range. The relief valve setting limits how high the pressure can go, often set about 10% below that to avoid nuisance discharges. For standard tanks, volume is calculated using Boyle's law, considering initial and final pressures and expected water expansion. For pressurized tanks, the math is simplified because the air cushion is pre-charged to the fill pressure. The tank's acceptance volume, the portion that actually compresses, must be large enough to hold the system's net expansion. If glycol is used, remember to increase the tank size because glycol expands more than water. The connection point of the tank defines the point of no pressure change, where pressure remains constant regardless of the pump's operation. That's why the tank is often connected on the suction side of the main system pump. Placing the tank higher can reduce the required static fill pressure, slightly reducing the tank's required size. Here's the golden rule of hydronic design: always pump away from the point of no pressure change. When you pump away from the tank, the pump adds its head to the static pressure, keeping all parts of the system under positive pressure. That prevents cavitation, eliminates air draw-in, and keeps flow stable, ensuring system longevity. If you pump into the tank instead, the suction pressure drops, and you can actually pull a vacuum on the return line. That can cause the water to flash to steam or suck air through automatic vents, both serious problems. So, the correct practice is clear: always pump away from the expansion tank connection. Let's review. Hydronic systems use water to carry heat efficiently and economically. Effective air elimination keeps the system quiet, stable, and long-lasting. Closed-loop pressurization prevents corrosion and allows higher operating temperatures. Maintain at least 4 psi at the highest point during filling. Correctly size and locate the compression tank to handle expansion safely. And always, pump away from the point of no pressure change. When these fundamentals are followed, A hydronic system becomes a smooth, silent, and reliable energy transfer network that will perform for decades. If you found this helpful, make sure to like the video and hit the subscribe button to this channel.